Combination circuits, RLC, if the capacitive reactance is greater than the inductive reactance. Again, as we are combining all the components in a single circuit in series, again we've got a total voltage that will separate and divide into a resistor voltage, an inductor voltage and a capacitor voltage. These three voltages will add up in accordance with their phase angles to total the supply voltage. When looking at the phasor diagrams, again the resistor will be at 0 degrees, the inductor will lead at 90 degrees in accordance with its voltage, and the capacitor will lag. Because the capacitor's reactance is greater, that means that the capacitive voltage will also be greater. The current flows is the same for all three of the components, as it is a series circuit, and when we combine these three we get that. Current is my reference. VR is on the horizontal, VL is on the vertical, and the capacitor voltage is downwards. We subtract the inductive voltage from the capacitive voltage, and that gives us a total reactive voltage across that level, which means my V total will be shown on that angle. So we can see, because of the capacitor, we've got the voltage lagging the current. When comparing the impedance graphs, see XC underneath, XL, we see capacitive reactance underneath, inductive reactance on top, we see the resistance towards the right, and we see the total reactance over there, and we see the total impedance on the diagonal over there. We will find that this angle is the same as that angle over there. When we calculate total voltage, that is equal to VR squared plus the difference between VC and VL squared, and then all of that rooted. VC minus VL, because VC is greater than VL, and we're subtracting them to get a positive answer. And then for the impedance, the same, Z is equal to R squared plus XC minus XL, that one squared, and then rooted. You can also use Ohm's law to calculate the effects over there. When placing the components in parallel, the capacitor connects parallel with the resistor, which connects in parallel with the inductor, which connects to the supply voltage. The total voltage is now my reference. As a result, I draw that on 0 degrees. We'll develop the current flow lagging, because the capacitive reactance is greater than the inductive reactance. More current's going to flow through the inductor, so that arrow is going to be greater. The resistor and then the capacitor with its leading current. And when we combine these three, we find the voltage on the horizontal along with the resistor current. Remember, as they are different units or different types of values measured in different units, the scaling between the voltage and the current does not matter as long as the current values are represented correctly. The capacitor leads its current by 90 degrees. The inductor lags its current by 90 degrees. And if we compare these two, that's about 1.5, that's about 3, so I will have reactive current over at that level, and then that would mean my total current would be on that angle lagging the voltage. So there I've got IL, there I've got IR, there I've got IC, and they all add together to give me my total current. In order to calculate, I total is equal to IR squared, resistor current squared, plus the difference between the inductor current and the capacitor current, both squared, and then that answer is rooted. Impedance, same as we had with in the previous part, 1 over Z is equal to the square root of 1 over R squared plus 1 over X C minus 1 over XL squared, all of that rooted. But as I said in previous parts, it's always safer to go total voltage over total current.